Question number 1. Three particles A, B, and C, each of mass m, are placed in that order in a straight line on a smooth horizontal table. The particle A is given the velocity u such that it collides directly with the particle B. After colliding with the particle A, the particle B moves and collides directly with the particle C. The coefficient of distribution between A and B is E. Find the velocity of B after the first collision. The coefficient of distribution between B and C is also E. Write down the velocity of C after its collision with B. A, B, C are placed in a straight line on a smooth horizontal table. A, B, C. Particle A is given a velocity u. Then A collide with B. After the collision, let W and V be the velocities of A and B. Applying I equal delta m V for A and B for the first collision. Zero is equal to mv plus mw minus mu. We have v plus w is equals to u. This first equation. According to the Newton's law of restitution, v minus w is equal to EU. This is second equation. 1 plus 2 implies V equals to 1 plus E times U divided by 2. Therefore, velocity of B after first collision is equal to 1 over 2 times 1 plus E times U. Then we have to write down the velocity of C after its collision with B. Let's consider the second collision. B collide with C with velocity V. Replacing U by V. Velocity of C after it collision with B is equal to 1 over 2 times 1 plus E times V. 1 over 2, 1 plus E. We can substitute for this E. 1 over 2 times 1 plus E times U. Then we have 1 over 4 times 1 plus E times square time U. Let's discuss about mark. 5 marks given for this equation. 5 marks given for this equation. And 5 marks given for this velocity V. And 5 marks given for this state, and last 5 marks given for final answer. Question number 2. A particle is projected from a point O on a horizontal flow with a velocity whose horizontal and vertical components are root GA and root 6GA respectively. The particle just clears two vertical walls of height A and B, which are at a horizontal distance A apart, as shown in the figure, so that the vertical component of the velocity of the particle when it passes the wall of height A is 2 root GA. So further that B is equal to 5A over 2. Particle is projected from O. Vertical component of velocity is root 6GA, and horizontal component of velocity is root GA. Then the particle passes the two vertical walls, height A and B. Distance between two vertical walls is A. When passing the first wall, horizontal component of velocity root GA will not change. Suppose that the vertical component of velocity is V. O, A, from O to A, vertically, V squared is equal to U squared plus 2 AS. V squared is equal to 6GA minus 2GA is equal to 4GA. V equal to 2 root GA. If it passes the second wall after further time t, then by applying S equal ut plus half at squared from A to B. First we shall use the equation for horizontal A is equal to root GA times T, implies T equals to A over G, root of A over G. Then vertically B minus A is equal to 2 root GA times T minus 1 over 2 G T square. Therefore, B minus A is equal to 2 root GA. You can substitute root A over G for T. G will cancel out. 2A minus A over 2. 3 over 2. B is equal to A plus 3A over 2. 5A over 2. Let's consider about marks. 5 marks given for this equation, 5 marks given for this equation, 5 marks given for this t, 5 marks given for this equation, and 5 marks given for the final answer. Question number 3. In the figure, A, B and C are particles of masses m, m and m respectively. The particles A and B are connected by light inextinguishable string. The particle C lying on a smooth horizontal table is connected to B by another light inextinguishable string passing over a small pulley fixed at the edge of the table. The particles and the strings all lie in the same vertical plane. The system is released from rest with the string tough. Write down equations sufficient to determine the tension of the string shown in A and B. First, we will draw the diagram and mark all forces and acceleration. A, B, C, M, 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 mg, that is weight of A, mg, that is weight of B, and capital Mg, that is weight of capital M. T, tension of this AB string, and T1, T1, then mark the acceleration. F, acceleration of B, that also F, acceleration of C. Applying F equal ma for each particle. For A, downwards particle mg minus T is equal to mf. This is the first equation. For B, vertically downwards, mg plus T minus T1 is equals to mf. Second equation. For C, horizontal, T1 is equal to capital MF. This is the third equation. We have sufficient equation for determine the tension of the string shown in A and B. Let's consider the about marks. 5 marks given for these 3 equations and 5 marks for forces. All forces should be there, and 5 marks for the acceleration. Question number 4. A car of mass m kilogram and constant power p kilowatt moves downwards along a straight road of inclination alpha to the horizontal. There is a constant resistance of r to its motion at a certain instance. The acceleration of the car is a. Find the velocity of the car at this instance. Deduce that the constant speed with which the car can move downwards along the road is 1000 p divided by r minus mg sin l. First, sketch the diagram for this sum. F is the tractive force and R is the constant resistance, and G with the weight of that car, and V is the speed of this car. F, tractive force, V. Speed of car. Applying P equals Fv, we have F equal P times 1000. P kilowatt, P times 1000 divided by V. At the instant when the acceleration is A, applying F equal ma downwards along the road. F plus mg sin alpha minus r is equal to ma. 1000 P divided by V plus mg sin alpha minus r is equals to ma. Therefore, V is equal to 1000 P divided by R minus mg sin alpha plus ma. When the car is moving with constant speed, A will be 0. A is equal to 0. Therefore, P is equal to 1000 P divided by R minus mg sin L. That is the final answer. Let's consider about marks. 5 marks for this step, 10 marks for this equation. 5 marks for this step V and last 5 marks V. Question number 5. Two particles A and B, each of mass m, attached to the two ends of a light inextensible string which passes over a smooth fixed pulley hanging in equilibrium. A small bead C also of mass m released from rest from a point at a distance A vertically above A, moves freely under gravity and collides and coalesces with A. See the figure. Write down equations sufficient to determine the impulse of the string at the instant of the collision between A and C and the velocity acquired by B just after the above collision. After coming C, B to the A just before collision, velocity of C is equal to Q. V be the velocity of B and A after the collision. J will be the impulse of the string. V velocity of C after collision. J impulse. Applying V squared equal to U squared plus 2AS. Downward vertical for C before collision. U squared is equal to 2GA. U is equal to root 2GA. J be the impulse in the string at the instance of collision. Now they applying I equals delta m v for B upwards vertically, J equal mv. This is the first equation. For A and C, downward vertically, minus J is equal to m plus m times V minus mu. That is minus J is equals to 2 mv minus m root of 2ga. This is the second equation. That is the third equation. There are three equations here, enough for the equation. Let's consider about marks. 5 marks for V and 5 marks for U and 5 marks for equation for A and C. This equation and 10 marks for the question number 6. In the usual notation, let 2i plus j and 3i minus j be the Gaussian vectors of 2 points A and B respectively. With respect to a fixed origin O, find the Gaussian vectors of the two distinct points C and D such that AOC equal to AOD equal to 5 over 2 and OC equal to OD equal to 1 over 3 AB. O A B OA is equal to 2i plus j. OB is equal to 3i minus j. OA is perpendicular to OC, that is AOC is equal to 5 over 2 and AOD also equal to 5 over 2. Therefore, AO perpendicular to OD and OC equal to OD. According to the vector triangular law, AB is equal to AO plus OB. AO means minus OA minus 2i plus j plus 3i minus j. Then we get I minus 2j. Then we can find modular of vector AB is equal to 1 plus 4 square root is equal to square root of 5. Let OC is equal to xi plus yj. OA perpendicular to OC. Therefore, we can consider about dot product OA dot OC 2i plus j dot xi plus yj should be equal to 0 because OA perpendicular to OC. Then we get y equals to minus 2x. OC is equal to 1 over 3 AB. Therefore, x squared plus 4x squared whole thing square root is equal to 1 over 3 square root 5. Therefore, x squared is equal to 1 over 9. Therefore, x equal to 1 over, in this case, y is equal to minus 2 over 3. And when x is equal to minus 1 over 3, y is equal to 2 over 3. OC is equal to xi plus yj, which means 1 over 3i minus 2 over 3j, and OD is equal to minus 1 over 3i plus 2 over 3j. Let's consider about marks. First 5 marks for this AB, and second 5 marks for y is equal to minus 2x, and third 5 marks for this, and another 5 marks for this, and last 5 marks for this. Question number 7. A particle P of weight W suspended from a horizontal ceiling by two light inextensible strings AP and BP, making angles alpha and 5 divided by 3 with the horizontal respectively, is in equilibrium as shown in the figure. Find the tension in the string AP in terms of W and alpha. Hence, find the minimum value of this tension and the corresponding value of alpha. First, mark all the forces on the strings T2, T1 for AP string and T2 BP string 5 over 6. Then we can use the Lami's theorem. By Lami's theorem, T1 divided by sine 5 minus 5 over 6. T1 divided by sine 5 minus 5 over 6 is equal to W divided by sine 5 over 2 minus alpha plus 5 over 6. Therefore, T1 is equals to W divided by 2 sine 5 over 3 plus alpha. Then we have to find the minimum value of this tension and the corresponding value of alpha. When T1 minimum, sine 5 over 3 plus alpha is equal to 1. That is the maximum value for the sine 5 over 3 plus alpha. Then we get 5 over 3 plus alpha is equal to 5 over 2. Therefore, alpha is equal to 5 over 6. Then we get the minimum value of T1 is equals to W over 2. Let's consider about the marks. First, 10 marks for this equation and another 5 marks for T1. 5 marks for all the forces T1 and T2 and 5 marks for alpha. Question number 8. A uniform rod AB of length 2A and weight W has its end A placed on a rough horizontal floor and the end B against a smooth vertical wall. The rod is kept in equilibrium in a vertical plane perpendicular to the wall by a horizontal force of magnitude P applied at the end A towards the wall. In the figure, F and R denote the frictional force and the normal reaction at A respectively. If the reaction at B from the wall is W divided by 2 as shown in the figure and the coefficient of friction between the rod and the floor is 1 over 4, so that W by 4 less than or equal to P less than or equal to 3 W divided by 4. For the equilibrium of this rod, we can consider the forces vertically and horizontal. For the equilibrium of the rod resolving passes into vertical direction. R minus W is equal to 0. Resolving passes into horizontal direction, we get F as P minus W divided by 2 equal to 0. This is second equation. Therefore, F is equal to W divided by 2 minus P. For the equilibrium of the rod, modulo of F less than or equal to mu R. We can substitute F for here. Modulo of W over 2 minus P less than or equal to mu R mean W. Mu for this 1 by 4. Therefore, we can substitute 1 by 4 for mu. That implies minus 1 over 4 W less than or equal to W over 2 minus P less than or equal to 1 over 4 W. Finally, we get the answer like W over 4 less than or equal to P less than or equal to 3 W divided by 4. Let's consider how to allocate the marks for this according to the mark scheme. First 5 marks for first equation and second 5 marks for second equation and another 5 marks for F and that inequality for question number 9. Let A and B two events of a sample space omega. In the usual notation, it is given that PA is equal to 3 over 5, PA intersect B is equal to 2 over 5 and PA dash intersect B is equal to 1 over 10. Find PB and PA dash intersect B dash, where A dash and B dash denote complementary events of A and B respectively. PB is equal to P A intersect B union A dash intersect B equal to P A intersect B plus P A dash intersect B. P A intersect B mean 2 divided by 5 and A dash intersect B 1 over 10. Then we get the answer as PB is equal to 1 over 2. P A dash intersect B dash is equal to P A union B intersect dash. P A union B dash is equal to 1 minus P A union P. 1 minus P A union B mean P A plus P B minus P A intersect B. Then we can substitute for the values 3 divided by 5 plus 1 over 2 minus 2 divided by 5. 1 minus 7 over 10. Then we get the final answer as 3 divided by 10 for P A dash intersect B dash. Let's consider the marks. First 5 marks given for this equation and another 5 marks for that answer and this 5 marks for the expression and another 5 marks for this statement and last 5 marks for the question number 10. 5 positive integers, each of which is less than 5, have 2 modes, one of which is 3. Their mean and median are both equal to 3. Find these 5 integers. With median is equal to 3 and 2 distinct modes 5 numbers which are less 5 in ascending order can be arranged in the following two possible ways. Can be arranged in the following two possible ways. A, 3, 3, 4. B, 3, 3, 4, 4. There are two possible ways. Since the sum is 15, as the mean is 3, 2a plus 10 is equal to 15. Then we get a is equal to 5 divided by 2. That is contradiction. O, b plus 14 is equal to 15. Then we get b is equal to 1. Therefore, 5 numbers are 1, 3, 3, 4, 4. Let's consider about marks. First 5 marks for this and second 5 marks for this. Then we get 5 marks for A and then 5 marks for B, and final answer